Well, in section 5 we talk about state observer design. Well, sometimes all the state variables are not available for measurement, either because it is not practical or it is impossible to measure the whole state. Note that sometimes the state can be measured, but this comes at a cost, because a sensor comes with a cost in terms of, well, really cost in euros, but also a cost of installing, calibrating the measurement, and also, well, you have to place it somewhere. You know that to apply state feedback control, all the state variables must be available at all times. So what we'll do in this section 5 is really estimate x hat, right? So this will lead to a so-called full order observer or a reduced order observer. So if, for instance, we have 4 states, x1 to x4, right, and only x2 and x4 are available for measurement, well, as we've said over here, you need the complete state. So there are 2 alternatives. The first alternative is a full order observer, and this will really estimate the whole state. Okay, so you'll have estimates for x1 hat, x2 hat, x3 hat, and x4 hat. Okay, you notice that, well, even if x2 and x4 are available for measurement, they are still being observed. This might make sense even if x2 and x4 are measured, because the estimates x2 hat and x4 hat will really be filtered versions of x2 and x4 using the model dynamics. Okay, so there might be some advantage in estimating x2 hat and x4 hat even if they are measured, well, simply because this full order observer will act as a filter. Of course, the other alternative, and this will use less computational power, is simply to estimate x1 hat and x3 hat. Okay, so we only estimate or observe what is not measured, and this leads to a so-called reduced order observer, right? And this, well, section 5 is of course important for the implementation of a state feedback controller if all the states are not measured, but it can also be imported independently of state feedback design, because the ideas of state observers can be used independently of control. You can use a state observer, for instance, to estimate x1 and x3 for which you don't have a measurement, and this will lead to a so-called soft sensor. So it could very well be that as an engineer you use the ideas behind section 5 on state observers to implement a soft sensor, that is a mathematical model that allows you to obtain an estimation of a quantity for which you do not have a measurement. Well, let us first start with the naive idea, and the so-called naive observer. So assume that we have a system that is described by the following state space representation. Here again this direct feed-through term is 0, and of course this is really always the case on a physical system. Well, the idea is that you run a virtual plant, a virtual model in parallel to the system, and that it receives the same input, okay, and then you will initialize the model at some initial guess x0 hat, right? Well, we can then look at the error, okay, that's the difference between the actual state x and the estimated state x hat. So we take the difference between this equation and this equation, and this is what we obtain. Remember, x tilde is the actual state minus x hat. Of course, this observation error is initialized in x0, the initial condition on the state, minus x0 hat, the initial condition of the virtual plant. If this is a matrix with eigenvalues that are to the left of the imaginary axis, well, you'll start from an initial condition x tilde 0, but since the system is stable, x tilde will evolve to 0. Okay, remember that this is the case if a has its eigenvalues to the left of the imaginary axis. So we had obtained that x tilde dot is equal to a x tilde, where x tilde is really the actual state minus the estimation, right? And we had seen that if a is stable, then really the observation error will go to 0 as t tends to infinity, and this is, of course, you can see it over here, independent of the input u of t. So that's the good news. Well, the bad news is, as you can see, it's impossible to affect the error dynamics. Okay, so the system might be stable, but it might be slow. So it is not possible with this naive observer to make sure that the error goes to 0 faster than you would have with the original system. Well, even worse news is that, of course, what could happen is that the system is unstable, and then, of course, it's impossible to use this naive observer. So what you see here on the screen is this so-called naive observer. So you take the state space description of the system and you run it in parallel to the system, and this is how you obtain x hat, right? Here the system is described here as a linear state space. In reality, of course, the system is most probably non-linear, so I should replace this in the most general case by a box with simply u entering and y coming out, right? So this is not necessarily linear, okay, it could be a non-linear system, and here in simulation here for the naive observer you use the linearized version. So the idea is that we start from the naive observer and that we try to improve on it, and clearly the improvement will consist in comparing the output of the system y with the output of the virtual plant that is run in parallel. Okay, this is here c x hat, and we'll have to compare this, construct an error, and use this error in some kind of feedback mechanism, and this is what is shown over here. You can clearly see here y, right, and this is the, well, y coming from the observer, and this error is kind of, well, using this feedback mechanism forced to go to 0, and this is then x hat, and this is the so-called full order Luenberger observer. So here is our full order Luenberger observer, an improvement on the Naïve approach, right? The Naïve approach is here in black, the first two terms, and the correction that is brought in here is shown over here. So it's L times the observation error, the difference between the measured output and the, well, estimated output, and this is this correction mechanism, right? So what you can now clearly see is that you have an x hat over here, an x hat over here, so you have a minus lc times x hat, you have the but over here, and you have the ly. This can then also be rewritten as lcx of t. But you can see clearly that the inputs to the full order Luenberger observer are, well, the control input and also the measured outputs, right? So we are again interested in the observation error. So we have the dynamics of the actual system, we have the dynamics of the observer, the full order Luenberger observer. So what we can do is write, well, x dot minus x hat dot, and this will be ax plus but, right, minus a minus lc x hat of t minus but, and you see that these two will cancel out, minus lcx of t, right? So you have here a minus lcx hat, but you have also a minus lcx. So you can rewrite this as a minus lc x tilde of t, and this is the observation error, so this is x tilde dot, and it's x tilde dot over here, right? So this is the equation that you obtain, and the main difference with respect to the naive observer comes from this term over here. And the advantage here is that you can use the matrix L to impose that this system is stable whatever the A over here. We have to impose that A minus LC as eigenvalues to the left of the imaginary axis, and we can use this L to make sure that the observation error goes to 0 with the dynamics that we desire. Well, there is, however, a restriction. We'll only be able to affect the modes of A minus LC that are observable. So if the pair AC is observable, then all modes are observable, and we're able to set the eigenvalues of the matrix A minus LC as we like, where we like. But of course what could happen is that there are unobservable modes, and those unobservable modes, well, you have to live with them and you cannot influence them, and of course you hope that they are stable, right? So in summary, it is possible to affect the observable modes of AC. So if the pair AC is observable, you can affect all modes. Well, you can stabilize the error dynamics provided that AC is detectable. This means that either AC is fully observable or that the unobservable modes are stable. We have the following statements which are equivalent. The pair AC is observable. Well, this is clearly the case as we have seen in the section on observability and controllability if the observability matrix, here it is, as full column rank. If this is the case, well, this means that you can assign all the eigenvalues of A minus LC freely by a suitable choice of L. And the pair that you'll obtain after full order observer design, A minus LC C, is still observable. Well, now we have, for the design of the full order observer, a design that involves the matrix A minus LC, and we have to assign the eigenvalues of this matrix. This looks a lot like the problem of, well, state feedback, where we had an eigenvalue placement problem involving the matrix A minus BK. So we had to assign the eigenvalues of these matrix. This looks like this one, but there is a difference because the L here is in front and here the K that we want to compute is in the back, right? And for this we have a command place, right? So if you do place A, B and the poles, well, you'll obtain the matrix K. So the alternative would be to write a second command, place L or something, to place the eigenvalues of A minus LC. But fortunately we have had a course on linear algebra, and you know that the eigenvalues of A minus LC is equal to the eigenvalues of A minus LC, the whole thing transpose, and you remember that AB transpose is equal to B transpose A transpose. So you can see that the eigenvalues of A minus LC are equal to the eigenvalues of A transpose minus C transpose and L transpose. So the difference is here now that this L transpose is at the end, and this looks like an eigenvalue placement problem like the one that we had before, right? So here you can see that we can use the same pole placement formula, the same MATLAB function, but we have to do a place with A transpose, C transpose, the poles of the observer here, and this will produce L transpose. Okay, so we'll use this command place that we had before. It will produce L transpose. Of course, we need not L transpose but L, but that's easy to fix in MATLAB. This is really an important slide because it has applications in your control laboratory. So what you can do now is combine the full order observer with state feedback, a state feedback law. U is equal to NR minus KX, and you obtain, well, so-called observer-based control. Here you can see that all the observed states are used. Okay, so remember in this situation where X was X1, X2, X3, X4, right? And where only X2 and X4 were measured. Okay, so this means that in this case here, the C, I don't know if you can see that, the C is really, well, you have two outputs, X2 and X4. It's 0, 1, 0, 0, 0, 0, 0, 1, right? So here in this case, well, in this observer-based control, what has been done is use really X1 hat, X2 hat, X3 hat, and X4 hat. But of course there are alternatives. So what you could do, for instance, instead of using x hat, is using a mix. So we could use, for instance, x1 hat. That's for sure. This one you need, right? Because it's not measured. But you could use, for instance, here the actual measurement x2 and here a estimation. Or you could use x1 hat, that's the constant, right? They are always there. x2 hat over here and here x4. Or you could use, and I think that's the last alternative, x1 hat, x3 hat, and you use x2 and x4, the measured states in your feedback. So what we can do now is write the equations that are behind observer-based control. So here the state space equations of the system. Here are the equations of the observer, the naive observer, plus the term that is using the difference between the measurement and the estimated output to, well, correct on the estimated state. And here the feedback equation, where now the state feedback is acting here on the full order observed state. As we know, we have the dynamics of the observation error that is over here, and if we inject this one over here, we obtain this equation over here. And remember that x tilde is x minus x hat, so x hat is of course equal to x minus x tilde. Okay, so this is how we replace x hat here by x minus x tilde. We group the terms in x, so this is a minus bk x. Remember that a minus bk, well, this is really the state equation behind state feedback, and we have a minus and a minus, so we have an influence also on x tilde and on the reference or set point input. So if we now construct a state which is really the original state x, and you add over here x tilde, the dynamics of, well, the observation error, you can obtain a state space description that is as follows. Of course, here you'll have x dot, x tilde dot, right? So here you have the evolution of x dot. It's a minus bk x, so you have a minus bk, right, plus bk x tilde, so you have a bk over here, and x tilde is, well, only dependent on x tilde dot, sorry, is only dependent on x tilde, so we have a 0 over here and a minus lc, plus a dependence on r. Okay, from this equation we have a 0 matrix over here, and we have bn over here. So this is the, well, full state space description of the system, evolution of x and evolution of the observation error. Here you see the state equation that is behind state feedback, and here you have the, well, state matrix, not state equation, state matrix. Here you have the state matrix that is behind observation. Well, we have just shown that the closed loop dynamics associated with observer-based controller can be described by the following state space representation. And if we call this matrix here a bar, well, we have to make sure that the eigenvalues of a bar are to the left of the j omega axis, And it's possible to show, because this matrix here is block upper triangular, that the eigenvalues of A bar are the eigenvalues of the two blocks that are on the main diagonal. So the eigenvalues of A bar are the eigenvalues of A minus BK associated with the eigenvalues of A minus LC. Right? A minus BK is associated to, well, state feedback, and this one here is associated to state observation, right? So therefore we have a separation, right? The design of the controller gain K and the design of the observer gain L can be done independently, and this is what we call the separation principle. So if we call this matrix C bar, this one A bar, and this one B bar, then you know, or you should know, that the transfer matrix in closed loop will be C bar Si minus A bar minus 1 B bar, and this is what we'll do in the next slide. So let us have a look at the closed loop transfer matrix, because the system here is clearly multivariable. Well, this is, as we've shown previously, the transfer matrix here, and this is again a block triangular matrix, upper triangular matrix, so its inverse is also block triangular, and on the diagonal you'll have the inverses of the elements that are over here. It's quite easy to show, so assume that we have a matrix here. Let's call it, well, A bar. I don't want to use A, X0 B bar, right? And we want its upper triangular, and we want to compute its inverse. Well, it will have the look A bar minus 1, B bar minus 1. So you'll take these blocks here on the diagonal, and you'll take these inverses, and here you'll have some matrix Y, and it's even possible to compute. If you take the product, you can clearly see here that you'll have identity matrix, you'll have an identity matrix over here, here you'll have a zero matrix, and here you'll have A bar Y plus X B bar minus 1. Okay, so this one here should be 0, so you can see here clearly that Y is minus A bar minus 1, X B bar minus 1. Okay, so we have just shown that if a matrix is upper triangular, it's a block upper triangular matrix, then its inverse is also block upper triangular, and on the main diagonal you'll have the inverses of the matrices that you find in the original matrix. Okay, so here we need the inverse of this matrix over here, so we know that we'll have also here a block upper triangular matrix. This is the case, and on the main diagonal you'll have the inverses of the matrix that are over here, and here we have, well, some matrix, but we are not really interested in what that matrix is, because you can kind of see, because of the 0 over here and the 0 over here, that this closed loop transfer matrix really will be influenced by this matrix over here. So this is the relation between the reference and the output, and you can see that it's the same transfer matrix that we have obtained previously in the case where we did have a state feedback based on the actual state. So you see here that in the closed loop transfer matrix there is a zero pole cancellation of the observer dynamics. The observer dynamics, they disappear from the closed loop transfer matrix. Well, there are a few other things that we can see, and there you have to have a look at this Kalman decomposition that we've considered previously when we were talking about controllability and observability. Clearly you can see that the observer modes are uncontrollable because you have the presence of a zero over here and a zero over here. Okay, so you cannot influence the observer error directly, and it cannot be influenced indirectly because of the zero over here. So the observer modes are uncontrollable. Well, the observer modes are observable. This is at least if the pair AC is observable, okay, so that the observability matrix has full column rank. And this can be seen by the fact that maybe, well, we have a zero over here, so it's not observed directly, the observer modes, but because of the presence of a matrix that will be non-zero, it will be observed indirectly through the observation of X. So the observer modes are observable as Y, and the measured output depends on X tilde, and this will be the case, of course, during the transient. So we have seen that the observer dynamics disappear from the closed loop transfer matrix, and that the estimator gain matrix L, well, does not appear in the closed loop transfer matrix. So L might seem irrelevant. However, this is not the case, because the observer gain L has indeed an effect, well, during the transients. Intuitively, if you have an estimation X hat, which is a poor estimate of X of t, then the control action will also be poor. So you should make sure that X hat is able to track the actual X sufficiently fast. And you can do this by using the following rule of thumb. So you should make the observer poles 5 to 10 times faster than the controller poles. In this way, X hat will be able to track X sufficiently fast that the control action based on X hat is good for control. So in practice, the observer gain L is limited, right? You cannot push the poles of the observer infinitely to the left. So you cannot make the speed of your observer as fast as you want, because of course there is a sensitivity to noise. Okay, the noise affects the measurement Y. So if you make the poles too fast, well, you'll have sensitivity to noise, you'll excite the noise. And also your observer is based on a model which is not perfect. Okay, so if you push the L too far, you'll end into problems. Don't forget that, for instance, high frequency resonances have not probably been captured in your model. This sensitivity to noise will not be visible when you work in simulation, for instance in MATLAB Simulink, unless you have added noise on your measurements. But it's very difficult to see, well, what kind of noise has to be added with what frequency content. So in practice, sensitivity to noise will not be visible in simulation, but it will appear as soon as you implement your observer and state feedback on the actual system. So it could be that when you implement on the actual system, you have to review your pole assignment. One way to test a state observer is to introduce an observation error x tilde at time 0 and see how fast it goes to 0. This is something that you can test during the control lab assignment. Indeed, in practice, the initial observation error will never be 0. Let us take the example of an inverted pendulum. When the observer and control are activated, it is assumed that the pendulum is perfectly vertical, phi is equal to 0. But in practice, this will not be the case. The angle phi might be a few degrees off, and the observer that will be starting from phi hat is equal to 0 will have to track phi. The observation error will go to 0 with a speed, a dynamics that will depend on the observer poles. As you can see, there is an interplay between the controller poles, the poles that you assign when you design the state feedback matrix K, and the observer poles, the poles that you use in the assignment to obtain the estimator gain L. This interplay you should bring to the front as much as possible during your control lab assignment. So we have seen that sometimes some states are measured, and it might therefore not be necessary to estimate them. We've seen also that sometimes, even if a state is measured, it might be a good idea to estimate it, because the full order estimator will act as a filter and you will have a filtered estimate. But in some cases, some states are measured and you do not want to implement the full order observer, because this would be too computationally intensive. Okay, so then you want to work with a so-called reduced order observer, and the idea there is to observe only the states that are not measured, and therefore you need a state space description where the state x is partitioned as follows. x1 are the states, and you can see it over here, that are measured, and x2 are the states that are not measured, and the idea is of course to only estimate the states x2. In the full order observer, you will have to work with a matrix A, right, that will be in Rn times n, and you're going to estimate all n states, right? And this will require working with a matrix A, and in the implementation this might be really computationally intensive. And we will see that of course if you work only to estimate x2, the dimension of the vectors and the number of integrators that you will need might decrease dramatically. For instance, it could be that in a reduced order observer you have only 1 or 2 of the states to estimate. Well, it might be interesting if you know that you have to design a reduced order observer, and remember this is the case in your control lab assignment, to be smart and use this type of state space description well up front. Okay, so remember that this is a state space description where the state is partitioned in x1 that is measured and x2 that is not measured, because if you do not use this state space description from the start, at some stage you will have to reorganize things for the design of the reduced order observer. Of course, this is still possible, but it will bring you some additional work. Well, I haven't told you before, but of course you'll have the same partition here for x1 dot and x2 dot, and well, this partitions the matrix A into the following matrices: A11, A12, A21 and A22, and there is of course a similar partition of the matrix B. Well, we can now start with the construction of the reduced order observer, and if you remember, the two equations that are important are x1 dot is A11 x1 plus A12 x2 plus B1u, and the other equation is x2 dot A21 x1 plus A22 x2 plus B2u, and this comes simply from this partition of the matrix A. Well, what we can do is see that the output is y, remember, identity matrix 0 x1 x2, so y is equal to x1, so y dot is equal to x1 dot. So from this equation you see that y dot is equal to this equation over here, and you can see here that, well, the output is known, the input is known, so you can reorganize things. This signal is known, right, and x2 is not known, right? So we have here an equation that plays the role in the full order observer. This would be equivalent to y is equal to cx, known unknown. Okay, so this equation here plays the role of the equation y is equal to cx in the full order observer. This is really an output equation, a measurement equation, and associated to this equation, well, you have the state equation of x2, and this is this equation over here, and we have rewritten it slightly, right? x2 dot is a22 x2, right, plus a21 x1, but x1 is y. Okay, so this is the state equation where the imported matrix is a22. It's the state matrix for the, well, equation or the evolution of x2, and these are two terms that are known. Y is measured and u is the control. So what you could do here is construct a naive observer for x2. Okay, so I'll call it x2 hat dot is equal to a22 x2 hat plus a21 y plus b2u. But this will not work for the same reasons as the full order naive observer does not work. So what we'll do is add a correction term that will compare, well, so an L here, it will be an L of course for the reduced order observer design. Well, we'll use this signal here, a12 x2 this comes from the actual system, and this can be constructed because we can obtain it from known signals. Okay, minus the A12 that comes x2 hat here, then that comes from, well, the reduced observer, and in here we'll be able to compare something that comes from the system that can be constructed from known signals, right, and something that comes from the observer. And this is how we're going to ensure that we can obtain x2 hat even if this matrix here is unstable, and that we can use this term here to influence the dynamics of the reduced order observer. So here are the equations that we had obtained in the previous slide, and well, this leads to the reduced order observer. Remember that this is the naive reduced order observer, and since we are not naive, well, we have to correct with an additional term that will compare, well, something that comes from the system with the equivalent signal coming from the observer, right? And well, this here can be constructed from signals that are known in the system, and we had seen that this is really A12 x2, right? And if you rearrange things, right, you can rewrite the equation as follows. Okay, so you have x2 hat dot minus ly dot, so we'll bring it to the other side, and you have terms in x2 hat, here they are, so A22 minus LA12, that's correct. You have terms in, let's put them in blue, in y here, over here, and so this will lead to A21 minus L11, and you have terms in u. Okay, here they are, and here they are, and this leads to B2 minus LB1. So remember that we had obtained the equation for the reduced order observer, and we can represent it as following, and this is how you're going to implement it, for instance, in MATLAB Simulink. So here we have the system, you have the control that is entering the system, and it's producing the measured outputs. Okay, so what we'll do is implement this equation, and the equation, you can see it over here. So x hat dot minus ly, this signal here, is indeed A22 minus LA12 x2 hat, this is this one over here, plus A21 minus L11 y, this is this one, plus B2 minus LB1 u. Okay, so this is how we obtain this signal over here. And of course, if you integrate this signal, right, you have x2 hat minus ly, and if you add ly over here, you have x2 hat, and this is really the signal, or the signal vector, that we want to estimate. It contains estimates of the states that are not measured directly. And as stated before, well, x2 will be a vector that in practice will contain maybe one or two states, so that in this integrator, well, you typically have one or two integrators. So this is really a vector integrator. So the computational power needed to implement a reduced order observer is of course much smaller, because for a full order observer you'll have something similar, but you'll have a need for n integrators, and n is in practice much larger than 1 or 2 states that need to be estimated in the reduced order observer. So we are not finished, because we have to have a look at the dynamics of the estimation error x2 minus x2 hat x2 tilde. And for that we consider the dynamics of x2 in the original system, the dynamics of the reduced order observer, and we simply take the difference between those two equations, and really what you'll have here is x2 tilde dot. Obviously you have this part over here, right, and then minus this part over here. You can see of course that these ones will cancel out, same for these ones, and if you have a look, you'll have a contribution in x2, right, and it will be a22 minus la12, so this is correct, and you'll have something similar for x2 hat, and we have the minus over here, so we'll have a22, right, and then minus la12. Okay, so here we have x2 minus x2 hat, and this is x2 tilde. Okay, so the error dynamics, they evolve using this equation over here, and providing that the pair a22 a12 is observable, then the eigenvalues of this matrix can be freely assigned by a suitable choice of L. Okay, so the observer is guaranteed to give an estimate of x2 hat which converges to x2 at the rate given by the eigenvalues of a12 minus L a12. So a22, sorry, minus la12. So you can see here that a22 plays the role of A in the full order observer, and that a12 here plays the role of C in the full order observer. So in order to implement this in MATLAB, what you first have to do is construct, of course, the partition of the matrix A and of the matrix B, right? And then what you have to do is place, use the command place, and then you'll have to, because it's an observer, work with A22 transpose, A12 transpose, take the observer poles, it's the reduced observer poles, you'll have to place, well, only a number of poles that correspond to the number of states x2 that have to be estimated. And what you'll obtain here is L transpose. Okay, remember that when you construct your reduced observer, you need not L transpose but L. And using this partition and, well, the implementation that I've shown you previously, well, you have everything that you need to implement your reduced order observer in MATLAB Simulink.